So welcome students. Today's topic is gas separation using membrane technology. So we have already studied the reverse osmosis process. In reverse osmosis process, we separate the salts from water or other fluids using the membrane. So thus we can also use the membrane technology for separation of the different gases. However, it is much difficult to separate the different gases using membrane technology in comparison to reverse osmosis process. Why? Because in reverse osmosis, the molecular size of salt, the size of the salt molecule is much larger than the size of the water molecule. But when you are separating the gases, different gases using the membrane technology, then the size of the different gases are nearly similar. Okay, and the membrane technology works on the absorption and diffusion phenomena. So it is very difficult to separate the gas using membrane technology. However, there are several commercial processes where we use the membrane technology for gas separation. Now we will start with conditions. So there are some conditions to which we can use to analyze the commercial viability of the membrane technology for gas separation. So first is the amount of the system or amount of the feed. So feed stream should be in range of 4.2 multiplied 10 to the power 3 to 57 multiplied 10 to the power 6 meter cube per day. So for commercial application you have to consider this amount of gas. For research purpose or for lab experiment we can use any amount of gas. Second is moderate concentration of more permeable gas in feed. So the concentration of permeating gas, more permeable gas should be in the range of 10 to 85%. So we cannot use this process to separate the minute amount of gas present in the system. Suppose you want to separate a gas which present only in the 1% or 0.5%, that is not possible by this process. This process is specifically used to separate the gas which present in the moderate concentration. Why? Because the permeability of gas, the permeability of membrane for both gases are nearly same. It cannot be very different. So you cannot separate the gas which present at very minute amount very efficiently by using this process. Okay. Next is the moderate to high pressure. So pressure of gas should be at the range of 18 to 137 atmospheric pressure. So why? Because in this process the pressure act as a driving force. So I have already told you that the gas separation is a pressure driving process. So here the driving force is the partial pressure of different species. So if the pressure of the gas is very low or low, then the driving force is very low, so you will not get the accurate amount of flux. Okay, and if the pressure is very high like 300 atm or 400 atm, then what's happened with you, your membrane cannot sustain that mechanical force, because most of the membranes used in this pressure in this process are the polymeric membrane. So you cannot use the very high pressure. So pressure should be at the moderate to high range. Third is the moderate temperature. So temperature should be 0 to 65 degrees Celsius. So again at very low temperature, because diffusion is the temperature dependent phenomena. So if the temperature is very low, then your diffusion is very difficult. Then again you will get the very low fluxes. And if the temperature is very high, then your polymeric membrane may not be sustained at temperature. Then last condition is acceptability of moderate recovery, less than 94%. So because this is a membrane based process, so here the recovery is slightly lower. So you cannot recover the 100% of desired gas from the system, or you cannot recover the 99% of desired gas. Okay, so here if the you are applying this process in a such a application where you need only the 90% recovery is acceptable, or the 80% recovery acceptable, then you can use this process. Otherwise If you want to separate the 100% gas or you want to separate the 99% gas, then this process is cannot be used. Now some application of membrane based process for gas separation. First is the H2 recovery from the purged gases. So purged gases are used to reduce the generally what is the purged gases? Purged gases are used to reduce the temperature of the reaction in the reactors, or purged gases are used to make the inert environment in the reactor chamber. So generally we use the N2 as a purged gas, or at the same time sometimes we use the gas as a reactant, like in some reaction we use the hydrogen as a reactant. So that hydrogen will mix in the purge gas, then you want to remove that hydrogen, which should be recycled in the reaction, and because hydrogen is a reactant. So we can use the membrane based process for separating the reactant from the purge gases. Or sometimes in most of the cases it is the hydrogen, because the molecule of hydrogen is very small than the nitrogen, so it is very useful to separate the hydrogen from the purge gases. Second application is the separation of CO2 from the natural gas. So we all know that when the natural gas comes out from the well, so it is not the pure natural gas. It contains the basically the natural gas contains the methane, hydrogen, as well as amount of CO2 and the water vapor. So what's happened, because the concentration of CO2 and water vapor reduces the quality of the natural gas. So it will reduce the calorific value of natural gas. Okay, so generally, and as well as it will also reduce the pressure of the well. Okay, because you are taking out the with natural gas you are taking out the CO2 also. So in most of the cases that CO2 is separated out from the natural gas, then it will re-injected to the well. Okay, so that will enrich the quality of the natural gas, as well as that will enrich the that will help to maintain the pressure of the well. Okay, so generally in the commercial scale plants we use the membrane based process to separate the CO2 from the natural gas. We have to also separate the water from the natural gas. For that we use the generally the compression process, but for CO2 separation we use the membrane based process. Third one most useful application of membrane based process is the air separation. Air separation in terms of nitrogen enriched environment and oxygen enriched environment. The most important application of this process is the providing the oxygen in the hospitals. So what's happened when any patient required in the oxygen, so that not required the 100% pure oxygen. In hospitals generally we use the 35% oxygen for the patients. So the oxygen so in the air the concentration of oxygen is around 21%. Okay, so for increasing the concentration from 21% to the 35%, we can use the membrane based process, because in here the requirement is to enrich the concentration of oxygen only. You need not to separate the oxygen and nitrogen entirely. You want to just enrich the concentration of oxygen. So for this purpose you can efficiently use the membrane based process. Next application is separation of SO2 from the smelter. Smelter gas contains a lot of SO2, which is a very dangerous pollutant for the environment, and the SO2 also leads to the acid rain. So you have to separate out the SO2. For that we can use the membrane based process. Similarly, we can also use the membrane based process to separate the H2S and water vapors from the natural gas. I have already told you, for that generally people use the compression process, but we can also use the membrane based process to separate the H2S and the water vapor from the natural gas. And next application is the separation of the or removal of the ammonia from the recycle stream from the ammonia synthesis. So in the ammonia synthesis, you know that the ammonia synthesis is a reversible process. When you react the hydrogen and nitrogen and produce the ammonia, it is a very reversible process, and the total recovery of ammonia is very low. So you will, in the product, you will get the ammonia as well as hydrogen and the nitrogen. Now the molecular size of ammonia is very larger than the molecular size of nitrogen and hydrogen. So you can easily separate the ammonia from the nitrogen and hydrogen using the membrane based process. Next application is the olefin paraffin separation. So you can use the membrane based process to separate the, like, ethane to ethene or propane to propene. So this olefins, propene and ethene, are used to produce the polymers, and these are the raw material of the polymers. So we can use the membrane based process, and this is now commercialized process. The membrane based process is commercialized for this type of separation. So you can use the membrane based process to separate the ethane and ethene. And the ethane is used for the like the fuel, and ethene will be used as a raw material for polymer production. We can also use this process for separation of the hydrocarbons and chlorocarbons from the flue gases. And if the flue gases contained, or the exhaust gases contains the unburned hydrocarbons or the chlorofluorocarbons, that can be separated out by using this process. This process, this is the repeated step, dehydration of natural gas. So we can remove the water from the natural gas, I already told you. Then this process is also used to dehydration of glycol. So when you produce the glycol in the vapor phase, so you can use the gas separation to remove the water vapor from the glycol, because the molecular size of glycol and molecular size of water vapor is very different. And again, it is all repeated application. Hydrocarbon separation you can use to separate the propane and propene. Now this is the schematic diagram of the membrane based gas separation process. Here you have the membrane. So here you have the one input and two output. So here this membrane based gas separation uh, is a pressure driving process. So here the molecule diffuses across the membrane due to the difference in partial pressure of that species across the membrane. So here we use the high pressure at the feed side, at the permeate side we use the low pressure. So due to the pressure difference, molecule will diffuse out from the membrane. So the feed enters from here, and it will the molecule will selectively diffuse across the membrane. Then you will get the rejected stream from here and product stream at the lower pressure side. Now we will discuss about the transport mechanism of the gas separation using the membrane process. So transport mechanism of the membrane based gas separation can be explained in the three different methods. So first is the Knudsen diffusion. So what is the Knudsen diffusion? So in Knudsen diffusion, the membranes are the porous membranes. So this is the Knudsen example of membrane. It is a porous membrane, and in the size of the pore is larger than the size of the both type of species. Suppose you have the two species. The molecule of the one species is larger, and one molecule of the other species is smaller. है So the pore size is larger than the molecular size of both species, but again but it will separate out the gas. Why? Because it is difficult to diffuse out from this pore. For the larger species, it is difficult to diffuse out from this pore. For the lower molecular size, it is they will easily diffuse out from this pore. Okay, so larger molecule cannot be easily diffused out, and smaller molecule can easily be diffused out. So you have the you have the partial separation from this process. Okay, so here the permeation is inversely proportional to the square root of the molecular weight. This mw is the molecular weight. So here the permeation is inversely proportional to the molecular weight of the of the different species present in the mixture, feed mixture. Okay, so for example, if you want to separate CO2 from air, then the molecular size of CO2 is larger and air molecular size of air is smaller. Air means oxygen and nitrogen. So molecular size of nitrogen and oxygen is smaller than the molecular size of CO2, carbon dioxide. So you will get the enriched air, nitrogen and oxygen at the other side of membrane. Okay, so this is the one transport mechanism. Second is the solution diffusion method. So I have already explained the solution diffusion method in the reverse osmosis process. In solution diffusion method, the diffusing or the permitting species first selectively absorbed on the surface of the membrane, then selectively diffused across the membrane, then dissolved the other side of the membrane. Okay, so here separation occurs due to the difference in the absorption coefficient as well as the diffusion coefficient of the different permitting species from the membrane. Okay, so generally, in solution diffusion model, we assume that membrane is non-porous. It is not, pores are not present in the membrane, and diffusion occurs due to the free volume theory, and absorption occurs. Generally, we use the Henry's law for absorption. So we will discuss it later. Now, diffusion coefficient cannot be as generally in solution diffusion model. We cannot assume diffusion coefficient as constant in general, but sometime it is constant also. And if it is not constant, then it will be the function of concentration in the membrane and the position. And sometime it may also depend upon the time. So we will discuss all the conditions later. Now, third type of transport mechanism is the molecular sieving. So in molecular sieving, the pore size are very small. It is the pore size in the membrane is the size at the range of the molecular size of the diffusing species. So in the molecular sieving, the pore size is very small. So only one type of molecule can pass through the membrane, and other molecule has the larger size than the pore, so it cannot pass through the membrane. So it is actually the sieving. It is not the membrane transport. It is actually the sieving. Okay, so there is a difference between the molecular sieving and the Kutzon diffusion. In Kutzon diffusion, the pore size are larger than the both molecules, but it is difficult to permeate for the larger molecule than the smaller molecule. But in the molecular sieving, the pore size are very small at the range of the in the range of the molecules itself. So only the smaller molecule can pass through the membrane and larger molecule cannot be passed through the membrane. Now we will discuss about the solution diffusion mechanism, which is the most popular mechanism to understand the gas separation using the membrane based separation process. Okay, so in the solution diffusion mechanism, there are two parameters which are most important. First is the glass transition temperature of the membrane, and second is the critical temperature of the gas. So the polymer properties depend upon the glass transition temperature, and permeant critical temperature. Permeant critical temperature means critical temperature of the gas. Okay, so what is the glass transition temperature? The glass transition temperature is the temperature where the polymeric molecules start the segmental movabilities. Okay, so when you go from the solid state to liquid state, so what is the difference in the solid state and this liquid state? In solid state, the molecules are present in the stationary form. In liquid state, molecules start to move, but polymers are the very large molecules. So in polymers, between the liquid state and solid state, there is one more transition. At that transition, the segment of the molecules start the movability. Okay, whole molecule cannot be displaced, but the segment of the molecule start the movability. That is called the glass transition temperature. So this transition is from the stiff state to the glassy state to the rubbery state. So Below glass transition temperature, the molecule of polymer is very stiff. It is like the steel wire, and above the glass transition temperature, it becomes the rubbery. It's like the thread or the rubber. Okay, so these two are important properties in the solution diffusion mechanism. First is the glass transition temperature of the polymer, and second is the critical temperature of the gas. So what is the critical temperature? Critical temperature is the thermodynamic property of the gas or the thermodynamic property of any material. So above, at the below critical temperature, you can condense a gas or you can liquefy a gas by simply increasing the pressure at a constant temperature. So if any gas is present below the critical temperature, like water vapor at the room temperature, so just if you compress the water vapor at the room temperature, it will become the liquid at higher pressure. Okay, but if if the critical temperature is, if the atmospheric or environment temperature is higher than the critical temperature of that material, then you cannot condense the gas by simply increasing the pressure without changing the temperature. So suppose air, so you cannot condense the air, or you cannot liquefy the air, you cannot liquefy the air by simply increasing the pressure of the gas. Okay, so this is the critical temperature. Okay, above critical temperature, fluids are critical point, the fluids are called the supercritical fluids. Okay, so air is a supercritical fluid. Okay, it cannot be condensed or it cannot be liquefied by simply increasing the pressure. Now based on these two parameters, you can classify the solution diffusion mechanism for the gas separation using the membrane process. So first type is, the when the your environment temperature or the temperature at which you are using the membrane based process is higher than the critical temperature of the gas and higher than the critical glass transition temperature of the membrane. So when you are talking about the glass transition temperature, it is a property of membrane polymer, and when you are talking about the critical temperature, it is the property of the feed gas which you want to separate out and the feeding species. Okay, so if the environment temperature or the temperature at which you are processing the fluid, at the temperature at which you are using the membrane based process is higher than the glass transition temperature of the polymer, and again higher than the critical temperature of the gas, then you can use the Henry's law to calculate the absorption coefficient of the gas at the surface of the membrane. Okay, and you can use, and then the second thing is the diffusion coefficients are constant. Okay, so here we can conclude, we can take that if the critical temperature if the environment temperature is higher than the critical temperature and the glass transition temperature, then you can use the Henry's law to calculate the absorption and desorption coefficients of different species at the membrane surfaces, and you can assume that diffusion coefficients are constant. Okay, now second condition is, if the environment temperature or the process temperature is less than the critical temperature of gas but higher than the critical temperature of the higher than the glass transition temperature. So in second condition, if your environment temperature or the process temperature is less than the critical temperature, means the gas which you want to separate out, that gas has the below critical temperature. Okay, and but your membrane is above glass transition temperature. For example, you want to separate out the different higher molecular weight hydrocarbons like butane to pentane or butane to butene. So these gases present at the room temperature, these gases are present in the below critical temperatures. You can, if you compress the butane, it will become the liquid. If you compress the pentane, or if you compress the propane, it will become the liquid. Okay, So these gases are present at the below critical temperature. If you want to separate these gases using the natural rubber membrane, so natural rubber is generally at the room temperature, where natural rubber is the at higher glass transition temperature. It is a rubbery, it shows the rubbery phenomena. It is the higher, it is higher above the glass transition temperature. So for this condition you can use the Henry's law to calculate the absorption and desorption coefficient of different feed species at the membrane surfaces. But the diffusion, at these condition, diffusion will be the concentration dependent. Okay, so is the at these condition, diffusion, you cannot consider the constant diffusion coefficient. Diffusion coefficient will depend upon the concentration of different species. Okay, now third condition. In third condition, suppose your gas is present, the environment temperature is below critical temperature of gas, and the below critical temperature of the glass transition, below glass transition temperature of the polymer. Okay, so at this condition, for example, you want to separate the organic vapor like C5 or C8 from the polyethylene. Not polyethylene, here it will be the, suppose polycarbonate. Polyethylene, the glass transition of polyethylene is generally the below environment temperature. So suppose you want to separate the organic vapor by using the polycarbonate polymer. So the TG of polycarbonate is well above the atmospheric temperature. Okay, so at this condition, the uh, Henry's law cannot be obeyed, because you cannot use Henry's law at this condition. And second thing is that diffusion will be concentrate, diffusion coefficient will be the concentration dependent. Okay, so in this condition, in the first condition, when you have the lower, your environment temperature is the higher than the critical temperature of gas and higher than the glass transition temperature of the polymer, you can use the Henry's law and you can use the constant diffusion coefficient. In second condition, when you have the lower the environment temperature is lower than the critical temperature and glass transition temperature, the environment temperature is higher than the glass transition temperature of polymer, then you can use the Henry's law, but diffusion coefficient will be the concentration dependent. And in third condition, if you have the environment temperature lower than the critical temperature of gas and lower than the glass transition temperature of the polymeric membrane, then you cannot use the Henry's law, and the concentration and um, the concentration will be the diffusion coefficient will be the concentration dependent. Okay, now the fourth point, if you want to separate a gas at the atmospheric temperature or at the environment condition, when the environment temperature is higher than the critical temperature, means gas is present in the supercritical form, but your glass transition temperature, but your membrane is present at the glass transition temperature is lower than the, but the environment temperature is lower than the glass transition temperature, means T is greater than Tc and T is less than Tg. Okay, so the environment temperature is greater than Tc, but environment temperature is lower than Tg, means your membrane is stiff. Okay, so for example, if you want to separate methane and ethane, so methane and ethane at room temperature present are the supercritical vapors. Okay, so or you want to separate hydrogen from air, or you want to separate hydrogen from methane in the natural gas. So these methane, hydrogen, methane, both are present in the supercritical condition, and you want to separate by using the ethylene cellulose membrane, polyethylene cellulose membrane. So polyethylene cellulose is present at the below at environment temperature present in the stiff, is the stiff. So glass transition temperature of this polymer is higher than the atmospheric temperature. Okay, so at this condition, you cannot use the Henry's law. Henry's law cannot be obeyed. And second is diffusion coefficients are concentration as well as time dependent. Now in this is the most difficult condition in the for the mathematical modeling, because your diffusion coefficient will be the function of concentration as well as the time. Now for calculating the for deriving the mathematical models for the gas separation using the membrane process, we have to calculate the permeabilities. The permeability is the most important parameter for the membrane transport using the for the membrane transport process. Okay, so here we have to calculate the permeabilities. So we will calculate the permeabilities for two first two conditions. First condition is when you can use the Henry's law and diffusion coefficients are constant, and second condition is when you can use the Henry's law and diffusion coefficients are the diffusion concentration dependent. Okay, yeah. So this is the diagram of the membrane based gas separation system. So here you have the high pressure side. Here pressure, suppose I is a species, so partial pressure of ith species is phi, and here the low pressure side, which is the product size side, here the partial pressure is of species ith species is pli. Okay, so this is the coordinate system. Here we use the x equal to 0, the thickness of membrane is delta. Here the here it is x equal to delta. Okay, so how the diffusion occurs in the across the membrane? First, in the solution diffusion model, first the molecules of the ith species absorb on the surface of the membrane. So when it will absorb, the concentration of that species will be Chi. Okay, here the partial pressure in the gases, generally concentration represented in terms of partial pressure. So in gas, the partial pressure is Phi at the membrane. After absorbing at the surface of the membrane, the concentration of that species at the surface of the membrane will be Chi. Okay, then it will start to diffuse across the membrane due to the concentration difference. Here the concentration is lower than the concentration at the feed side. So when it will diffuse, then the other side of the membrane, the concentration of ith species will become the CLI. Okay, so CLI is the concentration at the surface of the membrane in permeate side. Okay, in the lower pressure side. Now it will diffused, it will dissolved from the surface. So the molecule ith species, then the dissolved, it will vaporized from the surface. Then the partial pressure will of the permeate side of ith species will become the PLI. Okay, so this diagram shows the working of the membrane based gas separation. Now here it is written Chi is the concentration at the interface on high pressure side of component I, and the CLI is the concentration at the interface on the low pressure side of for component I. Now the flux can be represented by we can use the Fick's law to represent the flux. So Ji equal to minus Di dCi by dx, where Gi is the flux in terms of moles per meter square second, Di is the diffusivity coefficient, which is the meter square per second unit, C is the concentration of the component I, which is the unit will be the concentration is the moles per meter cube, then x is the distance or thickness of the membrane. Okay, so you can write this equation to this in this form, in the integral form. Now we will solve this equation for the different case. So in the first case, when the diffusivities of different components are constant and Henry's laws are applicable. So when it will occur, when your environment temperature is greater than the critical temperature of all gases, as well as greater than the glass transition temperature of the membrane. Okay, so if Di is constant, so you can simply integrate this equation. Okay, so xi become delta after integration. So Ji delta equal to Di, and when you integrate this, it will integrate from Chi to Cli to Chi. Okay, so you will get this equation. Okay. Now you can rearrange this equation in this form, Di by delta. Now you can apply the Henry's law. Okay, because in this condition Henry's law is applicable. So when you apply the Henry's law can correlate the concentration to the partial pressure. Okay, so here Chi can be written as Chi equal to Khi Phi, where Phi is the partial pressure of component I at the high pressure side, and Khi is the Henry's constant at the high pressure side. And similarly you can write the KLI equal to CLI equal to KLI multiplied by PLI. This is the Henry's law, है ना? So here PLI is the pressure of component I at the permeate side, and KLI is the Henry's constant of component I at the permeate side. So KHI and here KHI and KLI are generally the function of temperature only. The Henry's constant are generally the function of temperature only if your pressure difference is not very high. But if pressure difference is very high, then KHI and KLI may become the function of pressure also. Okay, so KHI and KLI may be equal if pressure difference is not very high, large. If pressure difference is very large, then both are different. Now let's assume that KLI and KHI are nearly same. At that condition, KLI KHI can be written as KI, and you can take it common from the bracket, and it will become Gi equal to Di Ki by delta Phi minus PLI. Here the driving force is Phi part difference between the partial pressure across the membrane. So this term Phi minus PLI, it is the driving force across the membrane, and Di multiplied by Ki divided by delta, it is the permeability, it is the diffusion, actually it is the coefficient or resistance. Okay, so you can define the permeability as Ki multiplied by Di. Okay, so this is the permeability measured from the experiment. Okay, so if you do the experiment at the different pressure difference, partial pressure difference, you will get a different flux. For a given membrane, you know the thickness of the membrane, so you can calculate the permeability across the membrane. So this is the final equation. Gi is the flux equal to Pi by delta Phi minus PLI. Now, if we assume that KHI is not equal to KLI, then what will happen? You can write Gi delta equal to Di KHI PHI minus KLI PLI. Okay, so this is your equation. This is the you can rearrange the equation in this form: Gi equal to Di by delta KHI PHI minus KLI PLI. Now this is the driving force is PHI minus PLI. So we just multiply and divide the PHI minus PLI, difference in the partial pressure of component I across the membrane, to this equation. Okay, now this whole term Di multiplied by in bracket KHI PHI minus KLI PLI divided by in bracket PHI minus PLI. This whole term becomes the permeability. Okay, so here Pi equal to this term in bracket. Okay, so here Gi equal to Pi delta Phi minus PLI, where Pi equal to this term. This is the condition where your Henry's constant are different at the both side of membrane. KHI is not equal to KLI. Now now we can consider the case 3. Case 2. In case 2, we assume that the feed species is present at the subcritical temperature, means environment temperature is lower than the critical temperature, but the membrane is present at the higher than the glass transition temperature. That means the environment temperature T is higher than the glass transition temperature. At this condition, your diffusivity will become the concentration dependent, but you can use the Henry's law. Okay, so at this condition, this equation can be integrated in this form, where di, this di bar the average diffusivity, average in terms of concentration. So we can take the average diffusivity coefficient in with respect to the concentration. This is the formula to integrate this equation. Okay, so again, if your if k value of khi and phi, here again we can use the Henry's law, where Chi equal to Khi multiplied by Phi and Cli equal to Kli multiplied by Pli. And again, if Kli and Khi are not equal, then you can use this formula and it will become Pi bar, where Pi bar is the permeability of component I across the membrane, and Phi minus Pli is the driving force across the membrane. Delta is the thickness of the membrane. And if Khi and Kli are equal, then you can write this as a Pi equal to, then Di become the D, and it will become Gi equal to Pi by delta Phi minus Pli. Now we will discuss about some engineering consideration in the gas permeability. So this is again the same diagram. Here you have the feed at the high pressure side. It will pass through from here to here and it will comes out from here. This is the rejected stream, and the molecule will selectively permeates through the membrane, and you will get the product from the permeate stream. Okay, so there are some engineering consideration in the gas separation unit. That is the one is the uh, stage cut, second is the temperature, third is the permeability, and fourth is the flow pattern. So what is the stage cut? Stage cut is amount of feed which is allowed to permeate through the membrane. Suppose your feed flow rate is Q and your permeate flow rate is P. So P divided by Q is the stage cut. So how much gas is permeates out from the permeate side, that is the stage cut. Okay, now temperature. Temperature is very important phenomena. Why? Because the Henry's coefficient as well as the diffusivity both depends upon the temperature. So if we change the temperature, your separation, the amount of separation changes, your as well as your amount of stage cut changes. Okay, so next is the permeability, and permeability I have already discussed about what is the permeability, and we will discuss flow pattern later. Now the membrane properties. So what are the properties membrane should require? What are the membrane properties required in this process? So first thing is a membrane permeability towards a specific component to be separated from the gas mixture. A high membrane permeability towards the specific component to be separated from the gas mixture, and high selectivity for membrane component relative to the other component in the mixture. So you need the high permeability as well as high selectivity. Why? Because its permeability is low, then your overall separation will be very less. You need the higher permeability. And if your selectivity is low, suppose your permeability is very high, a lot of gas will pass through the membrane, but your selectivity is low. Selectivity means how much separation occurs. Okay, if both molecules, both type of component will permeates through the membrane, then you will not get any separation. Okay, so you need the higher separation as well as the higher permeability. That is the desirable property of the membrane. Okay, so how it will occur? So permeability defined as the product of Henry's coefficient and the diffusion coefficient. Okay, so the separation occur if Henry's coefficient are different and diffusion coefficient are same. Separation may also occur when diffusion coefficients are different and Henry's coefficient are same, and separation may also again occur when the Henry's coefficient and diffusion coefficient both are different for the different component. Okay, so this is more, the third is more desirable condition. So your polymer, you have to choose the polymer in such a way that the Henry's coefficient or the absorption coefficient of the different gases present in the feed species and the diffusion coefficient of that gases in that polymer, both should be different for the different components. Now the other properties required in the membrane, it should be chemical, inert and physically stable. Okay, it should have the physical strength also. Okay, so and it should not be react with the it should not be reacted with the feed species. Suppose you are using the polyvinyl membranes for separation of the water-based system or the water vapor, then water vapor will be absorbed in this membrane. Okay, so you cannot use the such a membrane which will react with the feed species chemically or physically, as well as the strength of the membrane should be high, so it will sustain the mechanical pressure. Okay, now second thing is the absence of pinholes or other mechanical defects. Okay, so when you prepare the membrane, you should be cautious that it cannot contain membrane cannot contain any pinholes. Pinholes means there are some large pores in the membrane. When you make a very large membrane, sometimes it's happened there are some large pores in the membrane because you are separating the two gases, and the molecules of gases are very uh, the velocity of molecules of gases are very high. So if there are some pinholes in the membrane, so it will adversely affect your the separation. Okay, so there should not any pinhole in the membrane, as well as other mechanical defects. Other mechanical defects means sometimes it's happened that the thickness of membrane will change at the different part, so it should not happen. Okay, because it will affect the mechanical strength of the membrane. Now the separation factor. So here there is one more property which is defined as the separation factor or the selectivity. So selectivity alpha AB, it is defined as the PA by PB, where PA is the permeability of the component A and this is the PB. PB is the permeability of component B. Okay, if alpha AB is greater than 1, then A comes as a permeate. If alpha AB is less than 1, then B comes as a permeate. It is very simple to understand. If permeability of A is higher than the permeability of B, then your alpha is greater than 1 and you will get the A as a A will selectively permeates through the membrane and you will get the A at higher concentration in the permeate side. If the PB is greater than PA, then alpha AB is less than 1. At this condition, you will get the B component selectively across the at the permeate site. Now there are some rules given by the Michel in 1966 for the gas separation. The first is membrane is selectively permeable towards the component of gaseous mixture that has highest critical temperature and smallest molecular diameter or both. So generally this is the thumb rule. The membrane can selectively separate one component from the gaseous mixture which has the higher critical temperature, so the diffusivity will high, and second is the molecule size will be low. Okay, second condition is the selectivity of membrane decreases with increasing temperature, but fluxes increases with increasing temperature. Okay, so your permeability increases with increasing temperature, but separation factor or selectivity will decreases with increasing temperature. So if you increase the operating temperature of the system, so you will get the higher stage cut, higher output, but your quality of the product or your separation will reduce. Next point is stiff chain polymer membranes, although less permeable gas than for the gas, less permeable for the gases than flexible chain of polymer for the similar chemical constituent, are more selective towards the smaller molecules. So basically this tell that if you have the stiff membrane molecules, means that will be near to Tg or less than Tg. If polymer is present near to glass transition temperature or polymer is present lesser than the glass transition temperature, then the molecule of polymer will be stiff. So at this condition you will get the less flux, the amount or lesser stage cut. Means amount of gas permeates through the membrane will be less, but you will get the higher selectivity for the lower molecular weight compounds. Okay, so at stiffer membranes for give the less flux or lesser stage cut but higher selectivity. Now in next class we will study about the different type of flow patterns used in the gas membrane based gas separation process.